Hello everyone. In this video we're going to go through how to do a hypothesis test with your regression estimates. I'm going to assume that you've watched the previous video on regressions for correlation where we talked about the distribution of the estimates and the standard error of those estimates. If you haven't done so already, I encourage you to watch those and then come back here. A hypothesis test is a statistical tool that allows us to test beliefs about the population. Remember that we don't actually see the population, we have a data sample which is a subset of that population that we've randomly selected. This is going to allow us to assess claims about the population based only on a sample, and this is what we call inference. The overall idea with the hypothesis test is that we start out with a belief that we assume is true. We then look at the data and the result that we get from that data and ask ourselves, if our initial belief were true, how unlikely is it that we would see a result like the one that we got? A hypothesis test is going to set up some rules for us to make those conclusions. There are four main steps to a hypothesis test. Number one, we state the null hypothesis, that is our initial stance, and the alternative hypothesis. We then calculate a test statistic. Depending on what kind of hypothesis test you're doing, that calculation might be different. We're going to be talking specifically about regression hypothesis tests. Number three, we decide on a confidence level, and that's going to tell us what the rejection rule is going to be. We then compare the test statistic with the rejection rule, and then determine if we're going to reject the null hypothesis that we started out with or not. In this video, I'm going to be going through each of these steps in detail. The first thing that we always do in a hypothesis test is state our null hypothesis. We typically denote our null hypothesis as H0. That's H with the subscript 0, which is pronounced H0. H0 is a claim about the value of one of our population parameters. Those are our beta j's that we talked about in the previous videos, where beta j stands in for a generic population parameter that could be beta 0, beta 1, beta 2, and so forth. The null hypothesis is going to claim that we think that beta j equals some number. We'll call that C. Next, we write down our alternative hypothesis, denoted H1, which is simply the claim that the null hypothesis is false. So if the null is beta j equals C, then the alternative hypothesis is beta j does not equal C. It's worth mentioning here that the alternative hypothesis that I am using here is what we call a two-sided alternative. One-sided alternatives are also possible, but I'm not going to get into that here. Two-sided alternatives are by far the more common one in practice, so we will be focusing on that. One specific null hypothesis that is probably the most common one that we tend to see is the null hypothesis that a parameter, beta j, equals 0. This is basically saying that the variable that goes along with that coefficient has no relationship with the dependent variable. If beta j is 0, then that whole term just drops out of the equation. The alternative hypothesis then, of course, is going to be that beta j is not 0. That is to say that there is some relationship that exists between the variables. If we frame this in our bivariate regression, where we only have one explanatory variable, and our regression is going to give us the equation of a line, the hypothesis that beta 1 equals 0 says that the slope of that line is 0, or that we have a horizontal line. Step 2 of a hypothesis test is to calculate our test statistic. For the hypothesis test that we're going to be doing here, the test statistic is called a t-stat. To calculate a t-stat, we take our estimate, beta hat, subtract our hypothesized value, which we called C, and then we divide that by the standard error of beta hat. Remember that because of random sampling, our beta hats are going to be random, and therefore the t-stats are also going to be random. Specifically, t-stats have a probability distribution called the t-distribution, and if we're going to be really precise about these hypothesis tests, we're going to need to use that t-distribution. Remember, though, that if we have a sufficiently large sample size, n, the central limit theorem tells us that there's very little difference between the t-distribution and the standard normal distribution. That is, a normal distribution with a mean of 0 and a standard deviation of 1. We're going to continue on assuming that we have a large enough sample size to use the normal approximation. But I just want to let you know that if you want to be really, really precise about this, then we're going to need to use the t-distribution. Step 3 of a hypothesis test is to determine a confidence level. The confidence level tells us how sure do we need to be about a rejection of the null hypothesis. Remember that a hypothesis test starts out with the assumption that the null hypothesis is true, that beta hat in reality out there in the population is actually equal to C. When we look at the data, the estimate we get for that parameter is not necessarily going to be C. It's going to be some distance away from C. Now, if beta hat is far enough away from C, we might say, well, this is not very likely to happen given that the actual value we're trying to estimate is C. And the confidence level essentially asks, how unlikely is too unlikely? We might say, well, if the chance of this happening is less than 10%, then we're going to conclude that our null is not true. But we might also have a more stringent condition that where we say we need it to be less than a 5% chance of happening, or even a 1% chance of happening, or even stronger than that if we wanted to. The choice of this is entirely up to the data analyst to say how unlikely is unlikely enough. If we're able to reject at a very strict confidence level, then that's going to suggest the evidence against the null is very strong. When we talk about confidence levels, we typically state these as 1 minus p, where p is the probability that we consider to be too unlikely. So for example, if we chose p equals 10%, that it's a 10% chance of this happening, and we reject with that p, we say that we are going to reject with 90% confidence. The most commonly used probabilities are 10%, 5%, and 1%, so therefore we would say that the most commonly used confidence levels are 90%, 95%, and 99%. One of the main reasons that we're going to be using the central limit theorem here to say that our distribution is close enough to a standard normal is that we can use the critical values from the standard normal distribution and apply that to all of our situations without having to come up with new critical values for every single test. As I said before, this is an approximation, but as long as you have a relatively large sample, then these critical values are going to do okay. These are 3 numbers that are worth committing to memory. For 90% confidence, our critical value is 1.65. For 95% confidence, our critical value is 1.96. And for 99% confidence, our critical value is 2.58. The critical value is the number that we compare our t-statistic to decide whether or not we're going to reject the null. You can see that for higher confidence levels, we require a higher and higher t-statistic to cross the critical value and get the rejection of the null hypothesis. But if the t-statistic does cross those, then we have a stronger rejection. To finish up the test, we compare the absolute value of our t-statistic and see if it exceeds our chosen critical value. If the absolute value of the t-statistic does exceed the critical value, then we reject the null. If it does not, then we fail to reject the null. I've chosen this language very carefully because it's important to point out here that a failure to reject a null is not a confirmation of the null. All we can do with a hypothesis test is conclude that the null is false, or not conclude. That does not necessarily mean that the null is true, though. We simply don't have the evidence to claim that it is not true. One term that you might have heard in statistics before is statistical significance. Statistical significance is directly related to a specific hypothesis test where the null is that beta equals 0. Remember that beta equals 0 is the hypothesis that there is no relationship between x and y. If we reject that null, then we say that the variable is statistically significant. If we fail to reject, we say that it is not statistically significant. Now, it's also important to point out that statistically significant by itself doesn't actually mean anything. We have to state what our confidence level is. For example, if we were to reject the null that beta equals 0 with 95% confidence, then we would say that x, the variable that goes along with that, is significant at the 95% confidence level. To calculate the t-stat for a statistical significance test, remember that c equals 0, so when we subtract 0, we're just left with beta hat over the standard error. Since this is the most common type of hypothesis test we see in regressions, the Excel regression output actually gives us the t-statistics for this test, and you'll see those in the output when we go back to Excel. Let's do an example with our demand dataset of a hypothesis test. We're going to go back to the original regression we ran in the last set of videos where we estimated a bivariate regression for demand where we have quantity simply as a function of price and nothing else. We're going to test the hypothesis that the slope of our demand function is -7. That is to say, our null is beta naught equals -7, and our alternative hypothesis says beta 1 is not -7. That's step 1, stating our null and alternative hypotheses. Back over in Excel, we are going to calculate our t-statistic. The t-statistic is beta hat minus c. So beta hat here is going to be -9.5. That's our beta 1 hat. Minus c, so minus -7. The two minuses become a plus, so we get plus 7. And then we divide that by the standard error for beta 1 hat, which was 1.38, this one right here. So we get a t-statistic of -1.8. To finish up this test, we need to think about the critical values and whether or not our t-statistic exceeds those. First of all, we need to take the absolute value, so we get 1.813, and now compare those with the critical values from the standard normal distribution. For a 90% confident rejection, we need our t-stat to be above 1.65. That's true, so we can reject our null with 90% confidence. But this number is below 1.96, so we cannot reject the null with 95% confidence. This, of course, also means that we can't reject at 99% confidence, since we would need 2.58. I'm going to finish up this video with a visual representation for what a hypothesis test is doing. I've drawn a scatter plot of two variables, x and y. If I were to run a regression of y on x, then I would get the equation for a regression line that looks something like this, where the intercept is beta naught hat, and the slope of this line is beta 1 hat. So that's going to give me a regression line of y hat equals beta naught hat plus beta 1 hat x. In a hypothesis test, we're going to come up with a null that says h naught beta 1 equals c. This is saying that in reality, we think that the slope of the regression line is actually c. I'm going to arbitrarily draw in a line, something like that, and say that the slope of this line is c. So our null hypothesis is saying that the line actually looks like this green line as opposed to the blue line that we got from the data. Now, it's certainly possible that if the true slope of the line were c, we could still, randomly selecting data points, get those red dots in the sample that would lead us to seeing a slope of beta 1 hat, when in reality it's actually c. It's possible that that happened. But the question that we ask in the hypothesis test is, how unlikely is that to happen? Comparing the t-statistic to the critical values is what allows us to answer that question of, is this result too unlikely for the null to be true? I've drawn a picture of a standard normal distribution. That's going to be that classic bell curve. Remember that our critical value for 90% is 1.65. That means that 90% of the probability in the standard normal distribution lies between -1.65 and +1.65. If I draw on our graph -1.65 and +1.65, that tells us that the total amount of probability in these two tails of the distribution, that's this area and this area, add up to 10%. So that means we have 5% over here and 5% over here. And then we have 90% in this interior area. We can do the same thing for the 95% confidence level, where we need 1.96. In this case, the areas outside of -1.96 and +1.96, those areas together make up 5%. So we're going to have 2.5% probability out here. We're going to have 2.5% probability here, with 95% in the middle. And finally, for 99%, our critical value is 2.5 2.58. So we can do this again with negative 2.58 and positive 2.58, and the areas outside here and outside here add up to 99%. So we're going to have 0.5% over here and 0.5% over here. When we get our t-stat, then we are going to compare that t-stat with these three numbers and see where along this distribution does that t-stat lie. For another example, let's suppose that we have a t-stat of negative 2.2. This t-stat lies between negative 1.96 and negative 2.58. Or if we think about this in absolute value, it's between 1.96 and 2.58. So we can reject it with 90% since it's bigger than 1.65. Also reject it with 95%, it's bigger than 1.96, but it is not bigger than 2.58, so we cannot reject this null with 99% confidence.